我找你，我是哪？DK 对。
So will you just follow the schedule I emailed to you?
No.
No? So it's freestyle?
Freestyle. So all the questions will be answered by the technical details. Those are basically the questions. Lee will go ahead. So it's more introductions. So this is
不好意思，大家早安啊！我是台湾中心洪建啊，今天很高兴跟各位来分享这个 ADCP 的流量观测这个设备。那因为我们台湾中心的重要任务之一就是进行台湾期间的流量观测。那我们流量观测传统上有用一些比如说 propeller type 的 current meter。那这些比较侵入到水里面的量测仪器呢，有它的量测上的极限。那最近的话，美国SonTek的公司他们有一款新的 M9， 那这个它的量测的能力呢，比之前的 propeller type 的 current meter 高上许多哦。那因为我们很高兴请到这个SonTek的原厂技师 Mark。那他早上会跟我们讲一些这个SonTek M9 ADCP 的观测的基本原理，还要注意事项操作。那下午的话，还有另外一位技师叫做 Lee， 他会从英国 过来，现在在坐高铁，已经到机场。那下午的话，他会再讲更 advanced 后面的一些资料的 QA、QC。那我们明天的课程是到大甲溪福敦去，让各位学员实际操作这个仪器，早上去操作，获取一些资料，下午再回来这个电脑教室。那两位技师会教各位如何把这个资料读取出来，做后续的分析跟判读。OK， 那我现在把时间交给 Mark， 那我们是不是以热烈的掌声欢迎他？谢谢。
Thanks, Professor.
No.
Yeah, I'm very happy to be here in Taichung. I've been here, maybe 4 or 5 times, or maybe 6 times over the last 8 years or so. I'm based in Shanghai, China, very close to here. It's about 1 hour by airplane, and I travel frequently. So I'm based in Shanghai, and I service the Asia Pacific area for a brand called SonTek. And SonTek, by the way, how many people in this room are familiar with SonTek? Anyone has used our products before? Anyone? 1, 2, 3, 4? Okay, good. How many people in this room are familiar with acoustic Doppler, current meters, and profilers? Good. Same people plus 1 or 2. Okay, good. So I'd like to take this morning session. Let's discuss some of the basics, give some introduction to hydroacoustics. So hydroacoustics is the term that we use when acoustic instruments are used for measuring water. And that water could be water velocity, it could be water depth. These are different parameters that are used, and we use those to calculate a discharge measurement. On the screen here, you'll see a helicopter and some very clear water. This is in Greenland. One of the requirements when using acoustics, the fundamental principle of using acoustics is that we transmit, the sound waves into the water. And we use particles that are suspended in the water. We call those surrogates. And we assume that those are neutrally buoyant, so they're flowing with the stream flow in the river. And that the sound wave reflects off of these particles in the water, sediments. So this is a very challenging condition because this is Greenland, where the water is very clear and very pure, right? But we still had pretty good data here. The range may be less, but we had quite good data here in Greenland. So actually, the more sediments, the better for us, right? And I know in Taiwan, you have a lot of mud and sediments. But again, if there's too much sediments, the signal can be absorbed. Okay, so there are limitations on both ends of using acoustics. And when using acoustics, it's always important to understand the limitations before you go out into a river. Because not every river and not every condition you can use ADCPs and use acoustics. So part of my discussion this morning will be talking about where you don't want to use ADCPs. And that's just as important as knowing where you can use ADCPs. Okay, how to get good data. Because that's the goal of as users, is how to get high quality, good data. So we'll talk about that this morning and also this afternoon. So part of the fundamental concept is to measure discharge. As a hydrologist, you want to understand the total flow. That's the cubic meters per second. That's moving down a channel, moving down a river. In order to do that, you need to know the cross-sectional area of the section that you're crossing. You have to know that very accurately. The other measurement is the mean water velocity, right? Let me get a little bit closer here. But with a Doppler system, right, you're not always measuring the full water depth, right? There's a certain part at the top you're not measuring, and there's a certain part on the bottom that you're not measuring. Right? So there are some extrapolations at the top and extrapolations at the bottom, and then a chunk of water that we measure, the percent measure that we provide. So we'll talk about that as well. So when you combine the water velocity and the area, you get the discharge. And our software does that. Besides the M9, we also have other sensors that measure in different water conditions and different depths. So for example, in shallow water, which is a meter, a half a meter in a stream, we typically don't use this M9 in very shallow water, okay? We have another device called the flow tracker. This flow tracker was developed from a lab. Okay, so in hydraulics labs, maybe you're familiar with ADV sensors or LDV. This was based upon our ADV technology that's used in labs, small labs. And we made a field version of it, and we call that the flow tracker. So this flow tracker, you can see this is the transmitter here. It sends the acoustic signal out. There's a carrier frequency here. For this device, it's 10 megahertz. And that transmits sound out. There's particles in the water, and then reflected back to this arm and to this arm here. Because there's two paths, we call this a bistatic device. Later, we'll talk about the M9, and that's a monostatic device. Fundamentally, the way they process the data is different. But here you'll see a tag line that goes across the channel. And we divide it up into different sections. Right? So there is an ISO method here related to this, that each section should be not more than 5% of the total flow. So the way you divide up your channel, you have to make sure that you're getting 5% or less in each of the channels. So in the middle of your river, you may have more measurements. And on the edges where there's slow flow, you can have less measurements near the edges. Our software tells you if you're over that 5% threshold. It gives you a warning to make sure that you're at the ISO, you're following the ISO practices across. So this is for weighting measurements in small streams. So when you do the weighting measurement across the channel, we provide what's called a top setting weighting rod. And that weighting rod allows you to set the measurement at different depths. Okay. This is part of the method here. So if the water depth is, this is in feet by the way, so sorry it's not meters. But if it's very deep water, okay, if it's 2.5 and greater, maybe 2 points. And then depending on the depth, shallower, maybe 1 point. Sometimes it could even be 3 points. This allows you to set this at these different depths. Okay, so here's some examples here of taking this depth measurements here. Here's a little bit more of an explanation about a weighting measurement across the channel, where you see at each of the locations, we measure the depth. So on the weighting rod, it's graduated. So you see the water depth on the weighting rod. You put that into the flow tracker, and then for the velocity, we position it down. And we know our distance across the river. And that's how we calculate the flow tracker. It's very similar to what we do later with the M9 and what we do with other products, is how do we calculate, how do we get a very accurate measurement across this channel. Okay, here's an example about ADCPs. And this is an example of a bottom-mounted system looking upwards. Okay, and what we're doing is projecting the acoustics away. So with the flow tracker, it was going out and then coming back. And we call it bistatic because there's two different paths. With ADCPs, the signal goes out and then comes back on the same path. So we call that monostatic transmissions. And when we transmit, we pulse the signal. Okay? We're pulsing the signal. And that allows us to get cell data in the vertical or looking down or looking up because we pulse the data. It's also very important when you're using monostatic versus bistatic, is if you're in areas where there's different densities. Okay, so you could be near the ocean and you can have layered flow. You can have a saltwater tongue. In that case, monostatic is very good because the signal goes out and then maybe there's a change in density. The path may have a little bit of a change. Go, scatter, and then come back and follows the same path. So Snell's law in physics is applied here. So when that's very good about monostatic, because of Snell's law, change in density, no problem. The path will follow the same path going out and coming back. And because we pulse the signal, we get different depths in the water. Any questions so far? I think maybe half or 60% of the people in the room know some of this. So others, I'm giving a little bit of a brief introduction, so go a little bit slow. But traditionally, people have used mechanical current meters, okay? But obviously, you need a lot more. They need to be calibrated. There's a minimum threshold, right? So they won't, a very low flow, they may not turn. And you also can have what's called a cosine error. So going back to the flow tracker, we put the flow tracker in the water. We're measuring the water vectors along the channel, and we're measuring cross-channel velocity. So we're actually able to get the flow angle. So as we do our measurement across the stream, we're getting the corrected. So maybe there's a flow angle in the water. We're actually correcting it to get to the Vx, so the along channel velocity. So when you're using for the discharge calculation, you need to use the along channel velocities across. If you're using mechanical, the mechanical current meter may turn into the flow, right? So you get a cosine error, is what we call. So you may have an overestimation of the discharge by using mechanical. You get the total magnitude, a scalar value instead of the vector component. So in our discharge calculation, we use the along channel velocity. Same thing for this guy here. We'll talk about the M9 later. But inside, there's a compass. Okay? So as it turns, it knows its orientation. And we make these cosine corrections as we cross this channel. That's the importance of having a compass. Okay. So earlier I mentioned about the acoustic signal. So everything we do at SonTek is about acoustics and sound. So in the flow tracker, it's 10 megahertz signal. In this M9, which I'll talk about later, we have a 3 megahertz signal, very high frequency. We have a 1 megahertz, a little bit longer frequency. We have a middle beam, which is a very low frequency for echo sounding, for depth. Okay? And we use different frequencies to get different data at different depths. So very high frequency signals are absorbed by sound. Low frequency signals can travel much farther. So you can imagine if someone is in the other room, across the hall, okay? The high frequencies are filtered by this wall. Low frequencies would penetrate through this wall and go farther. So that's important in rivers that have a lot of mud or sediments. The low frequencies will travel farther than the higher frequencies. But again, it's about transmitting and reflecting out. Similar cases on a train station. Trains are coming by you. There's a shift in frequency. That's exactly what we're measuring, is change in frequency. So here's just some examples of an observer and then a passing train. You can see the compression of the signal. So if I'm standing here and there's a train coming towards me, the sound waves are compressed. And when the train passes by, they're stretched. So it goes from high frequency to low frequency as the train passes by. Very similar to the cases here with ADCPs. Okay. For the M9, and when we cross the river, so we can pull across. Maybe there's a bridge and we can pull the M9 across. We can have a remote boat. Okay. We could be even on a small boat and driving it across. But as we cross this channel from left to right, water depth, and we get velocity data as we cross. And we add up all of these pieces, all those squares have a dimension, a size, cell size, and has a water velocity. So our software calculates, it adds up all this data here and gives us the discharge. There are areas at the bottom and at the top where we don't measure, and we use extrapolation techniques. We use a power law extrapolation. In fact, our software allows you to use either a power law or to use a constant value at the top and the bottom. So we allow you that flexibility. So if you know the friction coefficient, or if you know the conditions at the bottom may be different, you can adjust for that. Or if there's a wind blowing and it's reversing the flow at the surface, we also can put values in for that. Okay. See, as you can imagine, there's a boat moving as well, right? So we have to compensate for the boat motion. So the measured velocity that I mentioned earlier up here, okay, we have to, what we're measuring total and what the boat is moving. So the boat is moving across and it's measuring. So what the boat is measuring is the composite of the boat motion and the water. So we need to remove the boat motion, okay? To remove boat motion, we have many ways to do that. One way is what's called bottom tracking. Bottom tracking is when the system is moving and it's looking at the bottom, and it's checking the bottom out and measuring the motion of the bottom. Okay, we call that bottom tracking. Another method is by using GPS. And so we have a GPS antenna which sits on top of the M9 to get motion. Bottom tracking is very accurate. Okay. With a DGPS, accuracy is about a meter with differential GPS. If we use RTK, we can get down to 20 centimeters with RTK. It's more expensive, but in small channels, that's very important to have 20 centimeters accuracy. In big rivers, yeah, differential GPS is okay, like the Changjiang or the Huanghe or the Zhujiang or Big River or the Dangshuihe. But on small channels and streams, then RTK is very important. Or if you want to do a survey of a section, then RTK is important. And I'll go into much more detail later with this. So far, any questions? This is a very basic just introduction, but any questions so far? And if I talk too fast, let me know as well. Or I can speak in Chinese, but it's很烂, not so good. What doing Thailand? So I prefer to speak in English if it's possible. Otherwise, I will speak like a 5-year-old Chinese boy. It's not so good. So my English is much better. So. Talk about the M9. So I'll just give a brief introduction to the M9, and then I'll talk more about measurements. This is our factory in California. It's in San Diego. It's a really nice place. We have 60 people. And our core markets are surface water, irrigation, oceanography, vessel navigation, and hydraulics research. A lot of the technology we do came out of the hydraulics research, the ADV technology, and we've moved that into the other areas that we serve. Irrigation is a very big market for us in California and in Spain, a little bit in Korea. In Thailand, we do a lot with irrigation. We work with the Royal Irrigation Department in Thailand quite a bit. Surface water is big in China. We have hundreds and hundreds of systems with the Shuilibu and the Huangbaoju, and here in Taiwan as well. the first instrument, we have a shallow water version. This is the M9. This is for water depths that are greater than maybe 10 meters, 5 meters. But the S5 is for shallow water, 5 meters and less, and it's a high frequency system. So the outer beams, the black circles, those are 3 megahertz. So that's a high frequency signal, 3 megahertz. The middle beam, that's an echo sounder. So that signal goes straight down to the bottom. And that's purely for water depth. Okay. The slant beams, it's a Janus configuration. That means 4 beams. Those are at 3 megahertz. And those are for water velocity, but they also measure depth. So when you're doing a transect, you're actually getting 5 data points at the bottom for depth. 1 is dedicated for echo sounding, and then 4 are dedicated for water velocity, but also can measure depth. Those 4 beams do what's called bottom tracking, and that's what gets the position of the boat as it crosses. So for the mid-range measurements, we have what's called an M9. This is a lower frequency system. So again, you see 9 beams. That's why we call it the M9. We have the high frequency beams for shallow water. So from 0 to 5, we use the high frequency. And then it automatically switches to the low frequency 1 megahertz systems when it gets above 5 meters, the water depth. And then from 5 to 40 meters, some conditions we can go to 50 meters for water depth, the velocity. The middle beam is a 500 kilohertz echo sounder dedicated for water depth. So that pushes through the mud to hit the bottom. Again, when we measure, we get 5 data points for soundings. We have another piece of software called HydroSurveyor, where we take the sounding data and we actually can make maps. So if you're doing a bathymetric survey of a river mouth, I know that David has done work in Tainan in some estuary, or you use the HydroSurveyor
Actually, I have to
in Kaohsiung.
Yeah.
There's a bay looking at the exchange of water. So you can use this M9 to do mapping, bathymetric mapping, as well as velocity mapping. Minimum depth for velocity is 6 centimeters. For the vertical beam, it starts at 0.2. So you can actually get really very low measurements for velocity. In the discharge calculations, you need to be in 0.3 depths of water. Okay. We also supply the system with what's called a PCM. This is a PCM here. These are 2 battery compartments. So this is our previous system. There was a screw-on cap. They would take battery pieces inside that. We've changed that, and we've added these two compartments here. So you can load it in 2 battery packs. Okay, with the system on. You don't need to turn the system on to change battery packs. You can swap one and put it in, and the system stays on by having these 2 battery compartments. So that's a new feature that we have here. And we have indicator lights on here. But that supplies the power. It also does the communications. So you can imagine that your boat is at a very remote location, maybe 200 meters away, 300 meters away, and it's being towed across the channel. And you're operating your software on your laptop. There's a distance. So there's a radio to control what's the data coming there. So there are 2-way communications. So we can control what's happening, and also the data can come back to our computer. And we use a high frequency radio, 2.4 gigahertz radio. It's Zigbee technology, the radio. And we use AA batteries. So that means that you can go out in Taichung and buy batteries, standard AA batteries, and we provide these canisters here. You load up the batteries, and then you go right into the slots. So it's a lot easier than before. here's some of the configuration here. We put the software onto a laptop. We now have just launched a version with a tablet. So we offer the Dell tablet, Windows 8 tablet from Dell. We can sell it to you, or you can buy your own tablet here in Taiwan, but load it onto a tablet, and then use, we also offer a zipped plastic bag, which is clear, so you can be in the field and it's raining and operating a tablet. No need to bring your laptop, because if you're worried about rain on your laptop, it's not so convenient. But we offer now a tablet version, so that this Windows software goes onto the tablet in this clear bag, and you can be heavy raining and still operating on this tablet your data. And then we have a dongle with a radio that goes to the system. So that's very nice if it's heavy rain or environmental conditions restricted. But in the system here, you can see the laptop. You can see a radio dongle and then how it communicates out. In the system here, we also have an RTK system. So you see this is what's called a tripod. And on this tripod, you see a GPS antenna here, and then this is the radio antenna here. That's put to the side of the river and connects, that data here is transmitted to the rover. So we call this the RTK base, and the data is transferred to the rover. And it takes the correction data from the RTK and does its correction position inside of the M9. Everything is processed on the M9. Okay? It's not processed on the computer. So in the past, 3, 4, 5 years in the past, all the data was transmitted to the computer and the calculations were performed on the computer. But it was risky, because if you lose the communication of the radio, you have to start your measurement all over again, because the calculations were done in the computer. Now, we've put an 8 gigabyte recorder inside here. So all the calculations and computations and processing and correcting for the motion is performed inside of the M9. So if you lose radio connection, you can continue your measurements and the data is recorded inside. And if you get your radio signal back, reestablish it, the data will come back after that. So you won't lose it if you lose radio.
No.
Yep.
So for camera is only for a Windows system, right? It's not providing for Android or AD before, okay?
Yeah, not yet for Apple and not yet for Android. So it needs to be a Windows-based system.
All right.
We also offer what's called a Castaway CTD. So on this M9, we provide a temperature sensor. Okay? So on the M9, we have a temperature sensor. Does anyone know why we put temperature sensor on M9? Anyone know? For velocity. Okay. That's right. Because the sound, as sound goes through a liquid or air, the speed changes depends on density. Right? So the speed of sound is a function of density. So in fresh water, temperature is the most important one. Right? But if you're in areas where there's seawater or there's intrusion, tongue forming, or different layers, then knowing the speed of sound becomes very important. So we have a device called the CTD, Castaway CTD. This is also from our company. And this is a device that you lower into the water, and you pull it back up, and it tells you the speed of sound in the water body that you're in. Okay. This device here has Bluetooth, and it would transmit the data directly back to your computer, and then update the data to make that adjustment for speed of sound change. So in this device here, we have a temperature sensor, platinum temperature sensor, and then we also have connectivity probes. Okay. So we're measuring temperature, we're measuring connectivity, and we're also measuring depth. So as it goes through the water column, it's measuring the temperature and connectivity and depth at different layers. From that, we calculate the speed of sound. Other users, maybe fish biologists or biology people, or other folks may be interested in the temperature, the stratification in a reservoir. So we have some users using Castaway for other purposes, not just for river discharge, but for other reservoir. They want to look at a reservoir and look at the stratification in the ocean. But for this application, we use it for the speed of sound to correct for the depth, to get your depth data very accurate. And I think in Taiwan, David, you have maybe 10 of these sold, or how many users do you have for this?
I think we have more than 10.
More than 10?
Yeah.
So I think on your computers here, you've loaded in the software. In the River Surveyor software, we have different setup tabs. So it's very easy to use. You go from left to right on the tabs. So on the far left tab is the Systems tab. And that tab tells you about what is the system, the serial number, the firmware, software. You can enter in the site location. So as you get to a site, you should maybe write down where it's located, the conditions of the day. That's the Systems tab. And then as we go across the bottom here, we have what's called a Samples tab. So as we're crossing this river, we're getting data, the position, the depth, the water velocity, and so we can get the data in a tabular form. So if you like looking at numbers, this is a great one. If you like numbers, this is the best tab. But most people don't want to look at numbers. Some people just like looking at nice pictures and looking at the vectors. That's the next screen, which is called the transect screen. So as you're crossing the river, you'll see a track, the boat track. Boat track based on bottom tracking, and then boat track based upon GPS. Sometimes there'll be a difference between the bottom track of the boat and the ship track based upon the GPS. And there's different reasons for that, which we'll describe. Sometimes the bottom is moving. So under very fast-moving water conditions, the riverbed actually can be moving. And that's called a moving bed. And that moving bed, very oftentimes, is not continuous. It's sometimes, and then it builds up in a mountain, and then it moves. It's just like in the desert in Africa, in the Sahara Desert. There's like dunes, sand dunes that form. The wind is blowing, and it makes a dune. At some point, it gets very steep, and then it breaks and falls, and then the sand moves on. It's very similar into rivers. You get these dunes at the bottom, and then there's a certain steepness, and then it moves down the river. So it's not, moving bed at the bottom is not always continuous. It's very discontinuous, and it's not easy to measure. So that's why we use GPS in those cases. Or we use another technique called stationary, which we'll talk about a little bit. Another tab on your software is what's called edge section. So when you're using a system like this, you get to the edge of the river. Okay? And you want to keep your boat steady when you start. So when you're at your left edge or right edge, you can select right or left. You can look at the data. You want to hold the boat steady, look at the data. And then when you stop the measurement, you cross and then you stop. You get the other section, the other edge. So we record all this. This is important for data quality. So we'll talk about that this afternoon, is having good data quality. So if you're at your edge and the boat is moving and you're doing this and you start, that can introduce errors into your discharge value. So it's important to, when you start your measurement, to be not moving, hit start, then wait 5 seconds, and then move the boat, and then stop, end measurement, wait 5 seconds, and then you complete your data. You don't want to be moving when you're starting and stopping. So that's important. And then we have what's called a navigation tab here. On this side of the screen, you'll see some tabular data as well. That will give you the area, that will give you the mean velocity, give you water temperature, and these are all configurable on your screen. You can go through and set up the way you want to have it. Our system has been automated for hydrologists. So we mentioned earlier about the three frequencies, the 3 megahertz, the 1 megahertz, the 500 kilohertz. This system it automatically transitions from very shallow water. So when very shallow water to deeper water, we automatically adjust the cell sizes and also the frequency to optimize for your measurements. So it's automatically adjusting here to optimize for resolution and also for performance. Okay. In the past, 5 years ago, you would have to use different frequencies. Okay. So if you're in shallow water, you would have to use a 3 megahertz. Well, you got to deep water, you have to change the ADCPs. So you needed to buy multiple systems. Okay. Or you needed to stop the boat. With this system here, you can automatically transition from shallow water to deep, and it compensates for this and adjusts the cell sizes and the frequencies. I know that researchers are interested in controlling this, and so in the afternoon we'll talk a little bit about that. So as you get near the edge, it optimizes on the high frequencies. You get very high resolution data. I've been in, I was doing some measurements in Korea, and I got cell sizes that were 3 centimeters in depth. It's very small cells. It was like a photograph looking at the river. And obviously, in the deeper parts, you get bigger cells. So this is that tablet I talked about